Dr. Anurag Srivastava is a Raymond and Lane Professor and Chairperson of the Computer Science and Electrical Engineering Department at West Virginia University. He's also an adjunct professor at the Washington State University and senior scientist at the Pacific Northwest National Lab. He's received his PhD degree in electrical engineering from the Illinois Institute of Technology in 2005. His research interests include data-driven algorithms for power system operation and control, including cyber resilience analysis. Today, he will be presenting his work titled AWR Metrics for Operational Resilience Monitoring using RT Air Mode.
Well, thank you. So good morning again. And I'm going to talk about AWR, which is stand for Anticipate, Withstand, and Recover. And we already heard about that why it is important, and how does it relate to resilience definition. I'll touch upon that and then talk about that how do we use that to develop a metric. So first, I think this is introductory, and we all heard about several different threats, which is causing a need for the power grid resilience. And over the years, if you look at the number of events, this is just for 2021. All the event which is causing billion-dollar disaster is increasing over the years, and our grid is even though upgraded with all the smart grid investment and everything, it is not the average life of different component is increasing too, which means the impact will be more and more unless we replace this, which is not going to happen. So we do need tools for that, and that's what I'm going to talk about. So we have worked on over the years, maybe almost like last 10 years, funded by different grants, several different kind of tools. So one is RPA, Resiliency Planning Investment Analysis. One is CPSAM, which is Cyber Physical Security Assessment Metric. And the recent one is DINGO, which is Digital Assistant for Grid Operators. This is based on NLP. But the one that I'm going to talk today is RT-MOD, which is Real-Time Resiliency Monitoring and Operational Decision Support. It does not have a cyber like a CPSAM, but I wanted to talk about this one because it goes into kind of fundamental of AWR and why Anticipate, Withstand, and Recover is important. Now, next, I'm going to talk about defining resilience, and then AWR metric, then RTR MOD tool, and then some test cases and summarize. So first one is defining resilience, and we already heard from the keynote today the definition of resilience. So that's what we are going to take, even though multiple definitions exist, and there is still more effort needed to make a standard, which is going on. There is a recent IEEE standard group started on defining resilience of distribution grid. We will see the report when it comes out. There are SIGRE effort, there are IEEE effort. This workshop is part of IEEE PES, which is one of the working group is Tools for Resilience, which I chair. And then there is other one within the IEEE, which also relates to resilience metric. And then SIGRE has two ongoing on resilience metric, and then so that DOE and NERC. So there are a lot of different efforts going on, but I think the one that I like is FORC definition, which is the ability to withstand and reduce the magnitude or duration of disruptive event, which include the capacity to anticipate. So anticipate is important, absorb or withstand, and rapidly recover from such an event. So these are three words which we selected to develop our metric. Recover, which we have been doing for a long time, right? So restoration process that exists in the grid, especially in distribution grid for the outage management and restoration, relates to recover. Now, recover to increase resilience is a different objective compared to recover to increase reliability, right? But that word is important. How do we recover? And once we define resilience. The second one is withstand, which means that when the event comes, how well I can withstand that event without having much impact on the system. And third one, anticipate, which is a little bit more far-fetched. We are not there yet, but we will eventually get there over years, is ability to predict the damage on the grid for any upcoming event. So if you think about it, we are still have to do a lot of work in terms of predicting wind, right? I mean, we did make some progress from 50% error to maybe now 30% error, but more work need to be done. Now, anticipating the impact on grid will require more data, infrastructure data, how, what is the strength of each pole, each substation transformer, which is not easy to get those data, and how it's going to stand different kind of event. And anticipate against cyber event is, it's very difficult, because we don't, attacker is not going to reveal themselves, they're going to hide themselves. So it will be challenging. But recover and withstand, we can at least do it. Now, taking those definition and then diving into AWR, which is anticipate, withstand, recover, we looked at anticipate and we found that this was the most difficult to measure. And the only way we can do is look at that how well utility is ready to anticipate, which means that they do have information which will warn them against weather event, or they do have information which will look at cyber and detect intrusion detection system and tell that where it's going to go next. And then once you collect all those factors, then we need to combine and give you a single metric. So we found, because these metrics are not physical system tied with physical system or cyber, so we found that CDC, Public Health Emergency Preparedness, the way they do it will be most appropriate. So we took that same method, which is weighted sum model metrics, applied to all these factors and integrated into a single metric. Next come withstand. Now we are talking about grid structure. So we can use the grid network, convert it to a graph. We can look at its control. We can look at where the resources are. We can look at where the loads are, critical loads are, and then we can compute some physical system metric, which will tell me that how well my system is going to withstand, which is all about redundancy in the system, right? How much redundancy we have. And if there is a load, critical load, like let's say hospital or airport, we can only reach to that load through one line. Of course, resiliency will be less compared to if I can reach it by closing additional normally open circuit in 3 different ways. Then the withstand will be higher, because if one is gone, I'm able to cover that. So we can use graph theory, multi-criteria decision-making process, which exists in other domain. In our case, we use analytical hierarchical process, AHP, to combine these factors with some weighted sum. And we were able to compute this withstand metric. The last one is recover. Again, it depends on your network, your ability to reach to critical loads from your resources. And then again, we can apply graph theory here. We can apply, but with more information, because event has passed. So we know that to recover, how soon I can reach to the outage load area using different resources. Again, that depends on the switches, control, resources, and load, and which we do have information on. So we can combine those and get the recover metrics. And then we can integrate all these 3 things, AWR with its own different factors. It is a busy slide, but the 3 things that I would like to point out is anticipate, we can get with multiple factor, withstand, we can get multiple factor, and recover. And then we call it AWR. Either we can integrate this further or keep it separate. So at different phase of event, we know that how does AWR metric looks like, and then we can go back to each specific sub metrics and try to fix it. So the advantage is that it is not only telling me metric, but it is also telling me why resiliency metric is changing and where I should focus on to improve that, right? So the root cause is also embedded in that. And these are the example factors, not everything included, but operator only see the top one, while engineers will see, our support engineers will see all the details and root causes why resiliency is going down. So there's definitely advantage in that, because this is system based, not performance based. So reliability metrics are performance based, because it tells you that what is the performance. It does not tell you why is that performance. while system-based metric should tell you that this is the performance and this is why performance is changing. So with AWR, we are capturing both. All right, so let's take that and then put that into the tool. So this tool is has several different things, system information first, because we are going to tie that into the control room. So we have ADMS, we might have OMS, outage management system. We want to take the data from there and redisplay it here so we know that the system data is right. And then resiliency monitoring, and then alert information service restoration, and then there is this decision support part. So there are a lot of different things. This one shows just how someone can use it to analyze, look ahead resiliency with two different options in this, and then choose the one which maximize the resiliency. So there are a lot of details in each of these tab, which we cannot go in detail today, but this tool is a working tool used by several different tool team in a trial, a pilot mode, and it can tell and predict the system impact and help making decisions. So here's one example for the it is stuck. So next I want to talk about the test cases. Well, looks like laptop is not that resilient as we wanted to. Oh, cool. All right, so here's the test case. This is islanded microgrid for 55 node. And what we did is that when we operate this microgrid, or mini grid, what do we call it, because it's large enough, we want to make sure that it is operated economic mode when there is no event going on, right? So if there is nothing happening to the grid, everything is normal, you want to operate that as most economic way as possible. When the grid is going to face any event, then we want to make it in resiliency mode, which is not going to be economic, because you need to be just like if you go from normal operation to secure mode, like N-1 secure mode in transmission grid, it is not going to be economic, right? It will cost you some money. So same thing here, if you want to change the resiliency mode to prepare for event, it will not be most economic. And that will require some decision to be taken, like, all the resources should be available when the event is going to come. So not use that, even though it is most economic to use ahead of the event. So in E mode and R mode, it shows the resiliency metric and how with the time progressing T-3, T-2, and T is the time when the event comes, it is going to change. And you can see that resiliency is going to change here as shown in the graph. So it works in terms of resiliency changing with different event scenario. The second case is two-stage proactive control. So here we want to use resiliency to guide our proactive control in advance of the event that is going to hit the system. And the whole idea is that if there are some different kind of switches, like automated switches and manually operated switches, we want to open that ahead of the event so that the system impact is minimized. So it does require some proactive control. And I'll not go into detail, but the results shows that if I do that, then resiliency metrics will tell me that worked. And by using the proactive control, my resiliency, which is the blue line, is higher than the red one if I do not take proactive control, right? So again, different scenarios, resiliency metric works. And also our load outage after the event demonstrate that this metrics driven control was good enough to do that, to avoid the impact. All right, so just to summarize, during extreme weather event or cyber event, situational awareness is very, very important, and that's what we're talking in this workshop today. And situational awareness driven decision support is, of course, that's the next step. For that, resiliency metric is needed to compare two different, alternative control action to compare the design, to plan ahead, and that can also help with not only corrective control but also proactive control, which will help. So RTR mod is one of the tools that we have worked on, which supports this. And with that, I would like to thank all my students and group which help, and especially DOE Solo Start project and UI Assist and so on and so on. With that, any questions?
Thank you so much, Professor Anurag, for the presentation. We have time to take some questions from the audience. Oh, there's one question there.
My name is Brandon from University of Tennessee. Thank you, Anurag, for a very interesting presentation. I have a big question. So, do you have any comment, or is there any effort to define how resilient is the resilient enough?
Yeah, I mean, that's a great question, and this is the question that I have got from several different DOE folks and also utility. I believe it's not possible, because we can only compare that this is where you are now and this is where you want to go, and how much it is enough, because these events that we are planning against, these threats, are also changing. So when we say resilience, we should always say against what, right? So because the dependency is so much on against what and for what system. So same thing cannot be applied. So benchmarking can be done only if we select system, only if we select threats, and then we can select the time, and then we can tell them, okay, this is how resiliency differ. So it's always comparative analysis, and still, which is very useful, but I think in absolute term we cannot.
Great. Any other question? We have time for one last question. Oh, yeah, the microphone is.
So Brandon from WAG. If I could just dig a little bit deeper on that, you really piqued my curiosity. So, as you think about anticipating, especially things like extreme weather events, one thing that we're really starting to learn is that we can't depend on historical information to help us predict future system behavior. So just kind of curious what your thoughts are on how we can maybe step up our game when it comes to anticipating and preparing for some of these major events on the system.
Sure, yeah. So that's again very good question, and when I was talking about anticipate, I said that's still far-fetched, which means that we need to wait for maybe a decade to get there a good anticipate. It's all about data. If we are talking about wildfire, we need to know that how wildfire is going to propagate in the system, and that requires vegetation, and that vegetation is, again, going to increase the wildfire propagation or not. So how does it going to burn that system? And if we can get that through satellite image, through local analysis and all those kind of things, that is definitely going to help. And we have seen that result while helping other utilities. If we talk about other event like a storm, then we need to know that wind speed and that each pole and how much wind that can withstand, right? So again, that requires data. I mean, the good goal will be, having a power grid in the same detail as Google Earth, where everything is 3D dimension is mapped, and then if we can get to that point, which there are some utility which have done that as a pilot phase, but if we can do it for the largest system, we will be much more able to do that with stand metrics and anticipate.